All right, thank you all for coming. My name is Zach Kurland, and I did research with Dr. Shi this semester, and my project was to construct and test a homemade vibrating sample magnetometer. So before I get started on my project, I want to talk about what a VSM is, a vibrating sample magnetometer. So a VSM allows us to find the magnetic properties of materials. So what happens is a sample, I need to use the laser probably. A sample is magnetized by a large electromagnet, which you can see here, as we lower it down in between its poles. And then it is vibrated in up and down motion in the proximity of stationary pickup coils. So what a pickup coil is it's a conductor or a cylinder that's wrapped thousands of times by a little tiny copper wire. And so when this magnetized sample vibrates in the proximity of a magnetic coil, an electromotive force is induced by a time-varying magnetic flux through the conductor itself via Faraday's law. And most importantly, this EMF is proportional to the magnetic moment of the electrons within it. And so the samples we're talking about that I used to calibrate this machine are very small. Right here, this is it, and it's relative to the size of a dime. But the ones that Dr. Shi and his students would use are much, much, much smaller. So why should we care about a VSM or the magnetic moment of electrons? Well, for one, it can be used by students in Physics 366, the intermediate experimental lab, to perform their experiments. But also, it gives us a thing called a hysteresis curve, which tells us about the magnetic properties of a material. So how the hysteresis curve works is, one, the sample is not magnetized, meaning that the net magnetic moment is equal to 0. And this means that all of the electrons in the sample are facing different directions. So we put it in between the magnet, and then we turn on the magnet and bring it all the way up to a very high magnetic field, a very strong one. At that point, that's when all of the electrons, or most of them, should be aligned in a uniform direction. So once we've done that, we then lower the strength of the magnetic field down to the point that it's at the mirror reflection of it on the opposite side. And then that means that as we're dropping it, the electrons in the material are going to start changing their directions until they're all facing the opposite direction at the bottom point. So at the extrema of this hysteresis loop, these are called the saturation points, and that's when the electrons no longer want to shift in any direction, they're all facing one way. And then, once we get to the very bottom, we bring it back up. And as you notice, there's a separation at the 0 value when the field is at 0. So that means here, the electrons were still facing some direction, but when we bring it back up to the beginning point, they don't want to be in the exact same spot, and this is what is called the hysteresis, is that it doesn't return to the same exact point as when it started. Another interesting characteristic of these graphs is that the area of the loop, if you were to calculate the area, it tells you about the actual energy needed to magnetize the sample in the opposite direction. And also, these two dots are tell us about the coercivity of the material, or how much, or what strength of a magnetic field can actually change the orientation of the electrons within the sample. So how did I do this? For one, I had to learn how to use a graphical programming language called LabVIEW. And that enabled me to control a lock-in amplifier, a Gauss meter, and an electromagnet. So the lock-in amplifier is here, and then here's the Gauss meter. And then the second part of the project was to design a device to load samples in between the electromagnet's poles, and also to be able to make a device that can hold the pickup coils in place. Then I needed to design an actuator holder, which is responsible for the mechanical vibration of the sample in between the poles, which you can see here. And this all needed to be done in such a way that the whole entire experiment is very reproducible, meaning that we know that every single time we load a sample in between the magnetic poles, it can come down to the same exact spot. And then the final test was to compare the magnetic moment ratio to the saturation point ratios for the easy orientation of the sample within the magnetic field. So the easy access orientation, or the easy orientation of a sample within a magnetic field, is one that allows the length of a sample to lie parallel to the lines of a magnetic field. So if these arrows were the magnetic field lines running from the North Pole of the magnet to the south pole, this little black bar right here would be parallel to those lines, and that's the easy axis. And that means that the electrons, they more easily align themselves in the direction of the magnetic field. So they're more easily changed by the strength of the magnetic field. Conversely, the hard axis would be if this little sample, the black bar running horizontal to the lines, was flipped 90 degrees and it would be vertical and then vibrated up and down between the lines. And so that hard axis is when the electrons would really resist the change in the orientation more than the easy axis. So this difference between easy and hard axis is due to something that's called anisotropy. And what this is that it's basically that there's different properties in materials when you look at them or you study them in different directions. A good example of this would be wood. It would be more easily split along the grain than across it, if you've ever had to cut wood before. So the next section of this presentation is my work on the sample holder, the actuator holder, and the positioning mechanism. So using 3D modeling techniques and 3D printing, I ended up designing this system. And so what this allows us to do is it allows us to put a sample at the tip of this holder and then lower it down next to a device that holds pickup coils. And so it will vibrate at a rate of around 40 times per second. I definitely slowed it down or else you wouldn't see anything. And that change, that vibration, is what induces the magnetic flux in the pickup coils, which would be held by these towers right here. So this is an extremely saturated image of my sample holder, actually attached to an actuator. So it did work. It came out very nicely. And it allows us to lower a sample that's attached to the end of this down in between the poles of the electromagnet. So the original actuator holder design we found was not really sufficient for our needs. The reason being is because it didn't really allow us to have precise positioning of a sample in the X, Y, or Z directions. And here's your Z, so that would be your up and down, your X would be out this way, your Y would be across. So the problem is that they're all coupled to one another, meaning that if I try to adjust one direction, I'm affecting the other two. So we don't really want that in science. We want to be able to say, if I adjust this direction, that's what's causing this, rather than having the possibility of moving the others. Also, this actuator holder is very unstable. It's just a couple of rods connected by horizontal ones with clamps. So every time we want to go and change the sample, you risk completely changing the orientation. And this device is so sensitive that the slightest bump can actually change the value. And you can see it changed on the lock-in amplifier as it's measuring it. So not very reproducible. So this was our first attempt to really try to fix that. So what we did is, with the help of Steve Anderson, we tried to utilize the frame of the magnet itself because it's extremely sturdy. It was really good at first because it allowed us to have the Z-axis adjustment. However, whenever we tried to adjust the X or Y, we would affect the Z's, so they were still coupled. You're able to, be able to adjust one, but you still couldn't adjust them all independently of one another. And so still, it was very hard to reproduce the positioning. So for our second attempt, we decided that we wanted to figure out how we're going to be able to adjust X, Y, and Z independently of one another. So what we came up with, Steve and I, is we made this leveled platform. So the surface of this blue platform is level to the floor. We added an extra rack and pinion, which allows us to adjust the X direction on this, the Y direction by this knob, which is across, back and forth, and then the Z direction up and down. So this successfully decoupled the X, Y, and Z positions. So this is also an extremely stable solution, and it allows for some really amazing precision. I mean, you can adjust it. It doesn't even look like it's moving. It's like micrometer precision. And you can see the values change on the lock-in amplifier, which is measuring the voltage. And most importantly, it proved to be very reproducible. So the next section of this are the results obtained. So testing the magnetometer to make sure it works. So this is a hysteresis loop I acquired from a single iron wire, which was 0.5 millimeters in diameter and 5.6 millimeters in length in the easy axis orientation between the magnetic poles. As you can see, the lack of pronounced hysteresis, or this gap in between the 2 points, shows that this sample is in fact a soft magnet, meaning that the electrons will more easily orient themselves when they come back to their original position. So before, like here, this shows that the electrons didn't want to come back to the same position, but here they were more easily coerced into getting back to the same spot. And this curve on the left that I obtained is from 2 cobalt wires, which were 0.5 millimeters in diameter and 5.2 and 5.4 millimeters respectively in length in the EZ axis. As you can see, there's more obvious hysteresis, or there's more obvious gap in between the 2 sides of the curve. And this shows that it is in fact a more a much harder magnet than the iron. Still not a very, very hard magnet, but more hard than the iron magnet. So that means that the electron orientation is not as easily changed by the magnetic field. So this is just a brief comparison of the two. We have the cobalt hysteresis curve on the left and the iron hysteresis curve on the right. So this is the real evidence that the VSM is working. So what we did is we compared the magnetic moment ratio of the 2 cobalt wires and the iron wire to their saturation magnetization values for the EZ axis orientation within the magnetic field. So what you do is you calculate the magnetic moment of the sample by taking some magnetization value that's characteristic of the material themselves, which you can find in a book or online. It's something that's a known value, experimentally found by scientists. And then you can multiply it by the volume of the sample, and that will give you a magnetic moment. So the magnetic moment ratio of the iron sample and the cobalt wires should be equal to the saturation voltage ratio for the iron and the saturation voltage for the cobalt. So these are the values I obtained. And then here's the ratio for the magnetic moment, and here's the ratio for the saturation voltage. And I found that the EZ axis saturation voltage was 2.48% off of the magnetic moment ratio, which means that it is performing as one would expect. And I want to give a huge thank you to Steve Anderson here in front row of the camera for his tremendous help and mentorship in the completion of this project. And obviously Dr. Shi, I think it was kind of obvious he's my mentor, but include him with the acknowledgements. But yes, thank you, Dr. Shi, so much for your advisement and help through this process. And I also want to give a shout out to Eric Deal, wherever he may be, for helping me actually discover Fusion 360, which was the 3D modeling technique that I used to design the sample holder and the and everything else. And also Scott Allred for making an attempt to try to print with a new material in Dr. Qual's lab when I didn't have the time to do so. Even when I was able to do that, he didn't have to. So thank you all.
Any questions for our first presenter?